Okay, let's go ahead and get started. Good morning, everyone. This is Jason Vandiver, Energy Code Program Manager for Spear. Um, Actually, it's we've got a labeled Speakers Bureau webinar series, but this is part of our SECO sponsored HVAC specific webinar series that we'll be doing. We'll be running at least 5 unique webinars. Most of them probably a couple of different times. Very excited to be bringing this one to you this morning. Alex Meany, senior trainer with RightSoft. I ran into him at the ACA conference, and in an hour of talking with him, I learned more than about HVAC than I've learned in a long time. He's a really sharp guy and has been doing it a long time. I mean, was in Hank's classroom back in the day. So I know everybody's going to learn a lot today, and I'm very much looking forward to it. So let's just some kind of updates real quick. So as always with the webinars, we'll hold the questions till the end. If you'll click on the little Q&A panel or the hand, I'll read the questions at the end, and we'll have Alex answer those. Just to let you know, we have the SECO-sponsored HVAC trainings. We have one scheduled for April 18th and April 19th in Austin, and I'll send a flyer out along with more information about all this with the course evaluation. If you do want ICC CEUs this morning for this course, just fill out the course evaluation, and Liz will get those CEUs to you. And then also I have on April 23rd and 24th, we have, it's a 2-hour live in-person training. Bring everybody breakfast. It's a pretty good deal. It's a free training. 23rd and 24th in Houston, one in April 26th in Uvalde. And then I'm talking to El Paso. Should have one scheduled in the middle of May in El Paso. I'm finalizing the dates now. There will be one in the DFW area, hopefully one down in the Valley. SECO is generous enough to sponsor 10 of these trainings, so there will be 10 live in-person, largely JS&D and the importance of it, JSD&T, and then a whole bunch of flex duct installation guidance and just some general residential HVAC installation training. Also, just everybody, here's my contact information down on the bottom. If you need any energy code trainings for your builders, contractors, whoever it may be, if you need contractor registration, permits, submittals, any sort of energy code related resources, just shoot me an email. I can get all those to you. If you're a jurisdiction that uses, the builders use third parties for IECC inspections, and you don't have time to make sure that those guys are doing their job, I'd be happy to do some free QA, QC of your third-party inspectors. Just let me know. Anything IECC related, please let me know. I'm happy to help you out. The price is right. It's free. Just FYI, the National Energy Codes Conference is in Denver. Everybody loves Colorado in May, right? May 28th to the 30th. And for code officials, I believe there's still a few scholarships available that will pay for the attendance of the conference. If you're interested in any of this, just mention it in an email to me, and I'd be happy to follow up with you on that. Next Monday and Tuesday in Austin is our annual conference. We've rebranded it, calling it the Spear Clean Energy Exchange. Covers a variety of efficiency-related topics in an interesting kind of, it's a breakout session format for the most part, rather than your typical presenter type presentation. And then on Tuesday, our keynote speaker, Dr. Catherine Hayhoe, supposedly is a phenomenal speaker. I haven't heard her yet, but looking very much forward to it. And actually, we've opened it up. If you're in the Austin area and just want to come for the keynote, you can come for free. That's Tuesday, April 9th from 11:15 to 2:15. Notice here, Dr. Hayhoe is a professor and director of Climate Science Center at Texas Tech University. So I'm also a graduate, as well as my wife, from Texas Tech University, and our first Final Four ever. So the important announcement, make sure and catch the game Saturday night. We got to beat Michigan State. And with that, I would like to turn it over to Alex. Alex, if you'll just hop on there and click screen share, we'll turn it over to you and be good to go.
All right, looks good. Recom Tech. Okay, we can see the screen there, Jason?
No, not yet.
Oh, haven't hit the final button there. How about that?
Yes, sir.
All right, beautiful. All right. Uh, so thank you very much, sir. Let's see. So we are here to learn why there's no such thing as like-for-like replacement. Don't worry, I'm not the kind of presenter who reads my slides to you, but let's see. I do want to go to the next slide, though. Come on, there we go. My name is Alex Meany. I'm the head trainer for RightSoft. I've been doing this for about a decade and a half, actually. I used to be their head of tech support. They made me the trainer 14, almost 15 years ago. And since then, I've just been running around the country teaching people. Well, the job was supposed to be originally teach them how to use the software because, they should know how to do the design stuff, right? They should know their manual J's and manual D's and manual S and manual T and all that. And, of course, nobody does. Not nobody, but very few. And so the job very quickly became teach them design and use our software to do it. And so, I immersed myself in the books and, pick the brains of whoever I can get my hands on, and eventually got myself officially certified. Did that EPIC class where you meet with Hank Rotowski. If you don't know who Hank Rotowski is, he's the guy who actually wrote the darn books. So I got to ask him a bunch of fun questions about the design process that a contractor's been asking me over the years, and get some little bit of clarification on that, which is great. And somebody back at my company did the math that I've trained over 10,000 contractors at this point, which I guess it didn't come as a surprise to me, but it's a bigger number than I would have guessed off the top of my head, I think. So just to let you know what we're going to be doing here, we're going to examine a home that currently has a 3-ton unit in it, right? And we are going to look at how the changing just a couple of settings in a building, just a couple of little things, like you change the windows, and you can see the difference between needing a 3-ton unit, needing a 2.5-ton unit, and how sort of delicate that balance is. I've always thought one of the ironies is that we really heavily enforce load calculations in the new construction market, where everything's predictable, right? Where if everybody's doing their job, we know how the building is being made. We know what the insulation is. We know what the minimum standards for the windows are. We know a lot of stuff. We know how well sealed the building is, how sealed the ductwork is, right? The big guessing games are out there in the retrofit market. And that's not where we're enforcing load calculations, right? Well, that's where I'm less likely to guess. You give me somebody with some experience, they can probably guess the load of a new construction. Now, I'm not advocating that, but if you told me, here, we're going to have a bet, you can win $100 if you can guess the load, I'd rather take a new construction house than a retrofit house any day of the week. So we're going to see how sort of how delicate that balance is. We'll take a look at that. Then we'll see how a 3-ton unit can take a home that only needs 2 to 2.5 tons, right? And I'm playing a dangerous game here, by the way. We're going to learn, hopefully if we get to do another session here that we have planned, we're going to learn really there's no such thing as a ton. Matter of fact, there's a trainer. There's a trainer who is, because I keep getting emails about him and I don't know his name yet, but he's going around Texas telling people that our software, the RightSoft software, is oversizing systems. Because he's look at this load. This is a 4-ton load, and RightSoft is saying it's 5 tons, and blah blah blah. And it's making me really, really, really angry because there's no such thing as a ton, right? And the example he's doing in his class, there are 5-ton units that are absolutely properly sized for that home, and then there are 5-ton units that would have been oversized, and there are 4-ton units that would have been properly sized for that home, and there are a bunch of 4-ton units that would be undersized, and so. Thinking that there's such a thing as a 3-ton home. That's why it's in, I'm going to try to put it in quote fingers as much as I can. I know you can't see me, but that is a thing. We're going to talk about, how it is that somebody might have a 3-ton unit in their home and be comfortable, even though that's more than what they need. And like I have up here, you get 3 guesses, and they should be duct, duct, and duct. There are other things that can cause this, refrigerant charge and bad thermostat placement, things like that. But mostly it's going to be duct work. So we're going to look at some of the duct systems that you might see in the field with some of these systems, and how that, how many CFM that they're realistically going to move. And then we'll discuss what happens when you move that amount of air through a new system. We're going to talk about what I like to call the perfect storm. The perfect storm is a single stage system, high SEER, kind of a value line piece of equipment. We'll talk about why that's important with a variable speed indoor technology, and why that combination can just end up being the worst for a system that was originally oversized and has been replaced like for like. And then, of course, even an imperfect storm, even something where it's not the perfect storm, it's still a storm, right? I'll show you the solution. Everybody knows what the solution is. Do a damn low calc, right? And make sure you're doing a good one, right? There's a bunch of different good ones out there. I'll show you the one that we do with our tool. We think ours is the best, but that's from the part of my job that's just going out there and making sure people are doing good work. I technically don't care which one you use. If you value time and money and efficiency, you come to us. If you value other things, maybe you go somewhere else. I don't care. And then how to reconcile what your calculation tells you with what you're seeing out in the field. So we're going to do all of that fun stuff. And where we're going to start is we're going to take this load calculation here. Right. So here's a building that I've already done the calculations for, right? And we're going to take a look at the load on this building, right? So, and unfortunately, when you are looking at a load calculation, some of the things that are easiest to tell about a building are the things that aren't going to have a huge impact on the load. So if I have a 21,000 BTU sensible load and a 2,500 BTU latent load, if I take my my load calculation and I change my building material, if I change my R30 ceiling to like an R19 ceiling, which you might have in a retrofit situation, that's going to bump the load up about 1,000 BTUs, right? And that's a big deal. It's not it's not nothing, but it's not the giant jump a lot of people expect it to be. If, on the other hand, the windows in the house are actually, recently replaced and have a U value, in the 0.3 range and a solar heat gain coefficient in that same range, that knocks the load down a good 2,000 BTUs, and is a lot different than and this, by the way, these starting off with low E windows to begin with, right? That's a bigger jump than we would otherwise have. And if you just change a couple of these factors, if you just change, go to this one. If you change those windows, right? Oh, this is the one with the duct design in it. No, it's all right. If you change those windows to clear vinyl windows, right? If you change those, that insulation to R19 instead of R30. If you just make, and then you make the house a little bit leakier, right? Just change those 3 settings. Before you know it, and by the way, it's the window factor that really drove this up. And probably changed the quality of the ductwork a little bit. You can drive this load calculation up a good, 6,000-7,000 BTUs. And the biggest factor involved there is one of the hardest things to tell is just by being able to look at the window. And there's some tricks to that and some energy science stuff on that. You guys, there's probably some training out there on how to do that. And if it feels like I'm sort of whipping through this a little bit, there's good reason for that. Given the group that we have here, I'm relatively sure that you guys are aware that you change from older materials to modern materials, you're going to lower the load in the building. The thing is, what you will sometimes have is a building that originally, right, built to as is, needed only say 2.5 tons worth of load. And what they got was a 3-ton load, right? What they got, right? Or what they got, not a 3-ton load. What they got was a 3-ton system, right? What they got was a 1200 CFM R22 system, right? And what I have here is what I have found in a lot of situations. So to be fair, I have not been up in a lot of attics in Texas myself. Matter of fact, well, that's not true. I've been up in a couple, but certainly not a lot, right? I was about to say I haven't been in any, but that's not true. I've been up in a few. One of the things I like to do to sort of improve my bona fides, if you will, is if there's time and inclination, I'll get my customers to, drag my big butt out into the field and let me see a thing or two out there. And what you see a lot of, and again, this won't come as a shock to probably most of the people in this group, is oversized systems, or who knows? Let's just put a big question mark on whether it's sized right or not. Right? Is what you see is underducted systems where they use these just terrible rules of thumb, right? The number of people. So it's great you guys are going to have that training coming up on, the best, practices for flex duct and whatnot. The number of people who use that sheet metal ductulator on flex duct is astounding, right? The number of people who think, oh, it's 6 inches for a bedroom and 7 inches for a master bedroom, and a 10 inch, or excuse me, an 8 inch or 2 6s for a kitchen, whatever. Like, they have these crazy rules of thumb that have nothing to do with, how many windows are there? How many outside walls are there? What's the load on that, right? They just size it however they're going to size it. And so what I did is I took this home, and I want you to look it over here a little bit. I took this home and I put a 1200 CFM system in here. And what I did is I did something that is not easy to do, actually, which is good. We on purpose, we didn't make it easy to do in our software. But I technically have the ability, and you should be happy to know that if I printed out the duct report, it would look really funky and weird and have all these bold italic numbers all over it that would let an inspector know that somebody has done this, because I've overridden all of these duct sizes, right? So what I've done is, I've put a 1200 CFM system in here, right? But then I went in and used the sort of crappy rules of thumb that people use to size a lot of duct systems, and 3-ton duct systems might typically get a system like this, right? When you start doing the math on like what you should have been sizing for, right? So if we just pretended, if I just did something like this, right, where we just sort of threw away, where's size? There we go. We just sort of threw away the CFM at every one of these registers. This system might not look crazy to a contractor, right? If I showed a contractor, like, hey guys, this is a 3-ton unit, and here's the duct system that's in the house, right? I'm going to have salespeople out in the field and contractors up in the attic looking at that and going, yeah, that's a 3-ton unit, sure, I'll buy that, right? Yeah, 7 here, 6s here, 5 there, yeah, okay, all right. And when you actually do the math, right, the difference between seeing it like this and seeing it the way I had it is when you actually show how much airflow you actually expect out of this 7-inch run that we're putting in a bedroom. There's just no way, right? First of all, the velocity on that would be almost 1,000 feet per minute, right? Second of all, 264 CFM out of a 7-inch flex duct is, if you could do it, the amount of noise that you would have from that would be, the thing would shake itself apart, right? And my personal favorite is the number of contractors who think, I got 1,200 CFM of air in this system, we'll put a 12-inch return on that, right? Like, I just, right? The velocity on this, by the way, 1,500, almost 6, that's closer to 1,500 feet per minute, okay? Standard for return air velocity, you want to keep that in a branch. You want to keep that maximum, depending on who you ask, 600, 700 feet per minute. This is over double, right? So two things, right? What's actually going to happen here? One, the system's going to be louder than people expect. It's actually a fun, when you got contractors who do really good work, one of the fun things they encounter is homeowners complaining that their system isn't running long enough, right? Well, my system isn't, my system isn't running. It's just not. Like, sir, ma'am, are you uncomfortable? No, but it's not running. It's not, he's like, you're not supposed to hear it come on, right? You're not, the experience you've been having in your home, we fixed that. You shouldn't have to turn the volume up on your television when the air conditioner comes on, right? So that's part of what's happening here. But part of what's really happening is if I take a look at a system with similar duct sizes, right? So if I open up, did I close my little folder? No, I didn't. Good. Let's see. Here's some realistic CFM that we might expect in this system. Sorry, it's being a little annoying. I think the screen share might be slowing me down. So what I did with this is I designed using manual D, and this is a proper design, right? I used the actual manual D calculations. I didn't tell it what sizes to give me. I assumed a really low pressure drop on my coil and a reasonably low pressure drop on my filter. So this is like, this is average, this is typical, right? And managed to get that friction rate to just about perfectly at 0.1 inches of friction. So this is sort of the most normal, no surprises, by the book, kind of almost rule of thumb, the kind of like that picture perfect thing when they cook up those rules of thumb that don't work, right? That's what this is, right? If I wanted to try to get systems, like I couldn't get this down to a 7. I can get it down to an 8. I couldn't get these down to 6s. I can get them down to 7s. I couldn't, I just gave up trying to get this to within anywhere near what that current duct system is. And I decided that I really didn't need to, because the way airflow works is if you reduce the amount of air through some of these components, they're going to give you a little less pressure drop, right? And so you're probably actually going to be able to move slightly more air through here if you wanted to. It's not advisable, but you could. But what I'm looking at here is a 650 CFM system, right? Not 1200, right? Almost half of that, right? 650 CFM, which would be right about, for R22 technology, it would be right about, it'd be hovering just at or maybe just above the freeze point of a coil on like its best day, right? If I start moving less airflow than this, I'm definitely freezing the coil, right? If I start moving this much airflow, I'm running the risk of it. But if I'm a lucky son of a gun, I might be able to move 650 CFM through a 3-ton unit and not freeze the coil. So this is right where this system is working. And this right here, this is why you can't change like for like, right? Because this is the reason why the homeowner has a quote unquote 3-ton unit running through their house and no actual comfort problems, right? So this is the thing, right? Right here, this is the trap. This is what will get a contractor. This is what will, and the contractor, oh, God bless them, they think the homeowner is crazy and scamming them and telling them lies when they say, you replaced my system and you made it uncomfortable in my house. Because of course, I replaced it with the same size unit you have. There is no like for like. It doesn't work like that. But okay, so how is it that a building might need a 2.5 or maybe even a 2-ton unit in their home by the book, by the manual J and S and all their powers, right? By the book, by the math, this home does not need 3 tons, but it's got 3 tons. How is it that the homeowner isn't aware that there's a problem? How is it the homeowner is having a comfort issue, right? Because you've asked some contractors, right? what happens when they replace like for like, and it turns out that the new system, is oversized? There are a lot of contractors who think that homeowner scammed them. There are a lot of contractors who think that homeowners will tell them it's perfectly comfortable in my house today, and they're lying. And when they replace the system with another bad one like the one they had, there was just this big scam the homeowner was running to try to convince the builder or the contractor to put something crappy in so they could blame the contractor and have them fix the problems from the last guy. That's not what's happening in most of these cases. This 3-ton unit is keeping this homeowner comfortable. And it's keeping this homeowner comfortable because of the low airflow. Okay? It's not rocket science. What happens to the capacity of a unit? I got to ask a bunch of rhetorical questions. I'm used to doing this when somebody can answer me. But what happens? I'll answer. What happens to a 3-ton unit, right, when you don't put 3 tons of air through it? What happens when you put significantly less air through an air conditioner? What happens to its capacity? It's going to drop. You're going to have significantly less capacity if you have significantly less airflow, right? You're not moving enough air through it for it to do its job, for it to do what it was rated for, okay? So that means, right, what happened, the big problem with oversizing a system is the short cycle, right? Oh no, it's short cycling, it's not running long enough. That means it's not going to do that moisture remover. That means it's not going to be comfortable in the house. That means all these bad things, right? Well, if you don't have the capacity that this 3-ton unit is rated for, you don't have as much short cycle as you have on the nameplate. The nameplate, man, if there is one thing I could change about the HVAC industry, it would be that everybody who gets into this industry should not be able to tell me. No one should be able to answer the question, how many BTUs are in a ton? Because we don't use ice, man. I'll talk about this in the next one that we do. But for crying out loud, there's no magic number. This isn't a refrigerator, right? A refrigerator, you plug it in and it makes things cold. That's it. This is a system with a bunch of working parts that all come separately and have to get put together in the right way to make it do its job, right? It's not a simple appliance. And so just because the unit's nameplate says 12,000 BTU, 36,000 BTUs, doesn't mean that's what you're getting. So if you're putting less airflow through it, you're getting less capacity. So instead of running 30 minutes at a time, it's running 45 minutes at a time. It's running 50 minutes at a time on a hot day, right? So it's not giving me the problems it would have given me otherwise. Okay, that's number one, okay? But it goes deeper than that, right? Number two, what happens to the system's latent capacity? All right, so I'm going to make an assumption here that not everybody, I'm assuming most of you know, but I'm not going to make an assumption that everybody knows what sensible and latent is. So sensible capacity is the ability to control temperature of a system. Latent capacity is the ability to remove moisture, right? Similarly, a sensible load is the load on the system that's raising the temperature in the house. And a latent load is the load on the system and the load on the home that's increasing the moisture level in the house, right? And so what is the latent capacity of a system? Depends on that system, right? So in our next session, these sessions all kind of lead into one another, so I don't want to give too much away. But in our next session, we're going to learn you can't trust AHRI, okay? It's not a designer's tool, full stop. If you're designing an HVAC system and you find yourself looking at AHRI information for anything other than does this meet the energy code requirements, you're doing something wrong, right? If you're ever looking at the capacity numbers coming from AHRI, you're doing something wrong. And the thing that should tell you, the clue, the reason you should have known that, and I'm not shaming people who didn't know that. Nobody's taught you that. That's fine. But the reason or the thing that should have been your first clue is AHRI doesn't tell me what the sensible capacity of a system is and what the latent capacity of the system is. It tells me total. And in reality, some systems can do a lot of moisture removal. Some systems can't do much at all. And you'll know that when you look at the sensibles and the latents. So anyway, what happens to the capacity a system's ability to remove moisture when you move less airflow through it? So on the contracting side of things, they all know that if I reduce the airflow, the coil is going to get colder faster. And it's going to tend to, while it's running, do more moisture removal. And that might not mean more BTUs of latent removal during the hour, but it means that when it's running, it does more moisture removal because the coil gets colder faster, okay? And so what happens when I have an oversized system that's underducted and I bring that airflow down almost to the point where I'm freezing the coil is I'm going to do a lot of moisture removal when it does run. So I have a system that's oversized, right? It's way underducted. It's oversized. My contractor's going out looking at the nameplate on the unit saying, all right, this is a 3-ton. Okay, cool. 3-ton, hey, homeowner, you got any comfort problems? Nope. We're snug as a bug in a rug, right? We're perfectly comfortable in this home. Great. And so you need a 3-ton. What they don't know is why the 3-ton is making that system, or is making that homeowner comfortable. And it's because we've choked down the airflow so much, they don't have an air conditioner. They have a dehumidifier that does some cooling, right? This thing is so good at moisture removal that even though it's not running for as much as it's supposed to be, it's able to keep up with the humidity control in the home, right? And what's going to happen when I come in here and I mean, we can just go back to the last one, man, because we know what's going to happen. What's going to happen when I come in here with what I call the perfect storm? So the perfect storm for me is when you are going to make a recommendation to the homeowner that, hey, you know what? We're going to lower your energy bills, Mr. and Mrs. Homeowner. We're going to sell you something nice and efficient, right? And so we are going to swap out your old R22 system here. We're going to replace it with this 410A system. So we're going to have to, we're going to do these things to it. And here's what this is going to do. We're going to teach you what SEER rating is. And we're going to say, we're going to increase this SEER rating. Right, the one you got now is a 10 SEER unit. We're gonna bring it all the way up to 16 SEER, right? That's gonna be really good for your energy bill. And here's all the nice things it's gonna do. So this matchup here is a 16 SEER unit, and we know you're on a budget, so we're gonna try to sell you one that's nice and efficient, but we're not gonna sell you the one that's got all the bells and whistles. You don't need all that stuff, But we noticed you had some airflow problems there, Mr. and Mrs. Homeowner. We think. You said that bedroom back there didn't always get as cool as you'd like it to. So we'd like to beef up your fan a little bit. We're going to sell you. We're going to say it just so happens that this matchup here with the high SEER rating, all the efficiency. Well, the most efficient fan they make is this variable speed fan, right? We're gonna sell you this variable speed fan. So here we go. We got a 16 SEER unit. It's 410A. It's got a variable speed fan. We're gonna put this sucker in, and we're not gonna change out your ductwork at all. Now, here's the problem with that. That variable speed fan is going to look at this duct system. It's going to go, I can do that. I got you, right? It's going to ramp up. First of all, it's going to sound like a jet engine, right? Second of all, that variable speed fan ain't going to last very long because it's under a lot of resistance. But that variable speed fan is going to, I think I can, all the way to the 350 CFM or 400 or 375 or 400 CFM per ton they set it for. And it's going to overcome all of that resistance from this bad ductwork. And now the thing that was making the 3-ton unit work is gone. The reduced airflow, it's no longer a factor, right? It's getting the airflow that it's supposed to get, right? Which you would think on paper is a good thing, but that's the only reason the old 3-ton was working. And now this variable speed fan that's doing its job, delivering the airflow that this thing is designed for, is revealing the fact, right? It's not now oversized. It was oversized before, right? But it's revealing the fact that it's oversized because we are now going to have massive, massive comfort issues, okay? Because all of this extra airflow is going to overpower the resistance, the static pressure loss of the ductwork. And it's going to cause these greater short cycles, right? So it was short cycling before a little bit, but now because it's getting better airflow, it's going to short cycle a lot more, right? And because when it does run, it is not doing the same amount of moisture removal, the moisture level in the house is going to start to really build up over time. We've seen situations where, you got a stack of bills sitting on a coffee table and they get damp just sitting in the middle of the room with the amount of moisture because what does the homeowner do when they're uncomfortable? Is they turn the thermostat down until they get comfortable. And they end up turning the thing down to 68, 65 degrees, which is enough to, on a stack of paper, pull a little humidity out of the air, especially if it's underneath the supply register, and right into that paper, right? Paper actually makes a good desiccant. And so the underlying issue was the reason why an oversized system was able to work, and replacing it with this particular kind of technology is going to be the perfect storm of discomfort. I mean, we're talking nightmare scenario discomfort, right? But it doesn't take that big of a change to reveal that, or to exasperate the underlying issue of the system originally being oversized. So some other things that can do. So let's say we throw away, sort of the variable speed fan aspect, right? So if we were looking at this system, right, and it's this crappy duct system, and it wasn't going to get 1,200 CFM per ton, right? And it wasn't going to get 650 CFM either. It's going to be, it's going to be somewhere you're getting like 900 CFM through the system or something, right? It's not as bad as this duct system is, and so it's going to do a little bit better, right? So because we don't have that variable speed fan, and also I've had contractors tell me, well, that variable speed fan, we can go out and we can just lower that fan speed, right? Because that's the right solution there, Bubba. Nice job. This thing is oversized, and so your solution is going to be, well, that's all right. We'll leave the oversized system and we'll just lower the fan. So that's not going to be the right solution, because and this is something I encourage contractors to tell homeowners, right? One of the reasons there's no such thing as like for like equipment swapping is that in a lot of the systems that are being swapped out. Now, this is starting to go away because the technology's been out for 15 years now, but we're still replacing a fair amount of R22 systems with 410A. And that's not in and of itself a thing, okay? That like, I can't across the board say, look, all R22 systems are like this and all 410A systems are like that. It's not how it works. Okay, but we have refocused the industry towards efficiency, right? It has, as we increase the federal minimum standards, efficiency becomes more and more important, right? I like to tell people, if you open the hood on a car built in the 70s, it's enough to make you want to cry. You can look at inside the hood of that car and you can see how every part works. You can see every little piece that has its job, and you got to identify what those are. And the inside of a car now, it's I think it's not even looking at the same thing anymore. And a lot of the reason for those changes is we've increased complexity to achieve efficiency, right? So we've done very similar things in the HVAC industry. We're driving toward more efficient. Well, some things had to go, right? The reason we preferred R22 back in the day is it got real cold real fast, right? And what they do now, like if you look at the like coils that we used to use, right? You could put a coil between me and you on a desk, and I could look through that coil from an old one. And I could, how many fingers am I holding up, and shine maybe a flashlight through there to help me out. But I could tell you, I can't do that with a new one. Newer coils are much larger. They have a lot more surface area, okay? And a big reason for that is to maintain efficiency. Well, when you got this very large surface area, what ends up happening is you end up absorbing heat relatively quickly, right? So, you know what the old rule of thumb used to be, right? Never use rules of thumb, but you know what the old rule of thumb used to be I have a moisture problem, Alex, right? We replaced this unit and, things are going bad, and, there's definitely a humidity issue in the house, and I done screwed up, and no, I didn't do a load, so, what are we going to do? I'm going to fix this problem. You know how I'm going to fix this problem? I'm going to put a bigger coil in there, Nope, don't do that. You see, back in the day, that was the rule of thumb. You want to do more moisture removal, you use a bigger coil. That'll do more moisture removal. And that's because the refrigerant technology we used got cold really fast. And so what would happen is you had more surface area, and it didn't get cold quite as fast because you were pouring more heat into that surface, right? Because you have a bigger area. But it still got cold pretty damn quickly, right? And over the course of the hour, having a larger surface area with a temperature below dew point, you would do more moisture removal in the long run, right? With a lot of modern systems, the time it takes for those systems to get cold, and we're coming up on my final point here, the time it takes those systems to get cold is longer, okay? When we compare ratings, right, and when engineers who design HVAC systems or literally design the equipment and match it up, they get a little, on edge when I start suggesting that their newer systems don't remove as much moisture. And I don't blame them, because they are spending a lot of resources making sure that exactly that does not happen, okay? They invest a lot of time and energy into doing everything they can to make this refrigerant technology that does not get cold as fast, by all things being equal, still is able to do more moisture removal. It's why you don't see 400 CFM per ton anymore, right? Most manufacturers have reduced the amount of airflow they design for to enhance the ability, especially on higher SEER units, because they have even more surface area, but to enhance the ability in that system to remove moisture. But what very few people or organizations are talking about, Florida Solar Energy Commission did a little bit of a study on this like 10 years ago. What they looked at was the ability of a system to remove moisture under part load conditions, AKA in a shorter than 1 hour cycle time. Because what all the engineers have done, what all the effort has gone into, is making sure that these systems can remove as much moisture as older systems do, which is, they didn't fully achieve that, by the way, in a lot of cases, but by and large, in the same ballpark over the course of an hour, because we do all of our equipment ratings over the course of an hour. So when you turn on an air conditioner, there are a lot of different technologies at play. Some manufacturers, and this is why when I put up my perfect storm, right? Right. That's not the perfect storm. The value equipment, the cheaper end equipment, tends to be a little more susceptible to this, because a lot of manufacturers are going to go and find ways to make their system better at moisture removal in a shorter cycle. Right. Some manufacturers, you turn on the condensing unit, there's a period of time when the fan doesn't even run. Condensing unit comes on, we're gonna wait a little while, we're gonna let things cool off a little bit. All right, now the fan's gonna kick on. Well, that wasted a little bit of energy transfer we could have nabbed, right? We could have said the capacity of the system was a little higher, but the manufacturer saying, you know what, we're willing to sacrifice that for it to improve its ability to remove moisture. In that 1 hour rating time, we're gonna sacrifice a little bit of that energy, not a lot, but enough that it does a little better moisture removal. Or you'll have other systems with variable speed fans that by default, no setup, no work by the manufacturer, it just automatically brings the fan on at low speed and slowly ramps up, and that allows that coil some time to get cold while I'm not pouring heat into it super fast. That's pistons versus TXVs. Now here I'm officially out of my own depth. Okay. But as I understand it, from the mouths of experts, piston-based systems are going to get colder faster and be a little less energy efficient, whereas TXVs take a little longer because they're kind of gradual as a result, though, they tend to extend that time before I hit dew point. And so it doesn't have to be that you have a swap where you went from PSC technology to variable speed technology, right? That 3-ton unit that they have could be keeping them comfortable by being underducted for a whole bunch of reasons. And if I come in there with just a regular old system right? Shoot, 14 SEER, you know, still PSC technology. What the hell? You know, we're just going to replace the most similar thing I have to what you have. I could have been on that on that knife's edge balance point that was keeping this thing comfortable. The existing system was getting cold enough, fast enough that in a 20, 30-minute run cycle, it was doing some moisture removal. Whereas a new modern system on a 20-minute run cycle, because the condenser comes on, the fan comes on, full blast, is doing minimal to no moisture removal, right? And unfortunately, there's no way for a contractor to even know that by simply looking at some ratings, because they only give those ratings for full run hour. All right. So what I want to do real quickly here is do a quick basic load calculation that I would do for a homeowner. I'm not going to put in customers' information or anything like that, but I'm going to show you all it takes is a little bit of effort to figure out what it is you're actually dealing with. So I'm going to design this system for Energy Star levels. I'm going to say it's a 1-story semi-loose home. And that's all I need to do to start this thing off. I normally would have put in, customer information and all that. But to do an effective load calculation, what I'm looking for in a load calculation tool, so we'll use the same house. It's 35 feet wide. It's about 28 feet deep, right? There's a garage over here, right? And we like this tool so much because putting all this information in, right, what that's actually doing on the back end is putting in the actual technical information, right? I never have to look at this page though, in order to do my real calculation. So I like to say that there are, oops, mistake there. I like to say that there are a lot of tools that are ACCA rated. Even the ACCA's, sort of guidelines on this will say, these are all officially approved tools, but they are not all the same, and that you should, what do they say? You should contact the software vendors to find the differences and things like that. So we, and if you take a look here, this is all I have to do for, to do the load calculation for a replacement. I just need to do a block load, right? And what I need to do is I just need to be able to take a quick look and say that this is a slab floor. I need to be able to take a quick look and say this is an R30 ceiling. I need to be able to take a quick look and say that these walls are R13, which they are, right? And I want to be able to take a quick look and say the ductwork is in the vented attic, and it is a radial system, and it's a radial return, and it's not that well sealed, and it's not that well insulated. Right, and just make those adjustments and be able to change the load. This is the key, in my opinion, to evaluating software, is how easy is it for you to say, hey, you know what, actually all of these windows are not lowy windows, right? How easy is it for you to do that? And the majority of these windows are 5 feet tall, right? The devil in the details, right? That these are 3 by 3 foot windows, right? That this is a 5 foot by 3 foot garden window. Right, and I can individually change that out. Oh, that's the wrong button. Garden window, right? And at these 2 windows here, they're 6 foot by 7 foot sliders, right? Because when you start looking at, and these are all 3 by 5, and you know what? These windows here in the front of the building, they have an overhang over them, right? There's a 5 foot porch with a foot of vertical separation on the front of the building, and so I can plug that in. And you know what? In fact, I'm going to put in some internal shade on all the windows. Why not? Right? I'll say that the windows have 45-degree blinds with 50% closed. And the one other thing I have to do is just tell it how many people are in the house and what's my baseline appliance load. And with this tool, if I set the orientation of this building here, right? I think the building, I have my original plan. Yep. That's a dotted every I, crossed every T, looked at every detail, load calculation. I lied. I have to make the garage unconditioned. Sorry. All right. That's what I get for looking at my plan notes or my presentation notes while I'm doing it. The ability to be able to go in and change some of these individual factors to reflect the reality. That's why we started with, it only takes a couple of changes in a retrofit job to change a load, right? And I'm just throwing this little tiny plug in here for us. You can do, if you're ACCA certified, you can do this, full stop, right? If you're ACCA certified, you have the ability to make these changes. How realistic is it that you're going to, right? Is this tool something that tells you that if you give me an address, we'll give you a load? Or is this tool something that makes you go into a back-end spreadsheet and find it somewhere in a giant pile of numbers, right? Or is this tool something that I can be like, this one right here is different, and then change it? And that's why we like ours so much, right? That's why I like ours so much. I don't know how everybody else feels about it, but and so once I have these numbers and I look at the actual load of my building, I can make an educated decision as to what this system will be, right? I can decide whether, okay, look, there's no way this is a 3-ton unit. I'm not putting a 3-ton on this. Okay, now what do you do? Or, so I need to put a 2.5, or I need to do this, I need to do that. You know, what are we going to do about that? That becomes sort of the topic for our next discussion. The fact that no load calculation can be called a 3-ton load. What you do next is you do manual S. What you do next is you figure out what the capacity of a system that you want to recommend will be, and you compare it to how it matches with the load. But that's a story for another day. Okay, so I know that's a lot of information in a relatively short period of time. I hope we have some questions to clarify anything that I might have made confusing. I apologize if I did.
No, so there's a ton of material. It's kind of hard to eat it all at once, but that's why we're having you back. I'm really looking forward to the manual, getting into the weeds on the manual S. I do have a few questions.
Okay.
How would a system be sized on an existing residential structure? Scenario: HVAC replacement for 1,800 square foot home, unknown window rating, but a double pane metal frame. Insulation in the walls is unknown. I'm assuming you'd guess R13. And ceiling insulation appears to be R30. So I think you fairly well covered that, but if you want to speak to it a little bit.
So a couple of things, right? There are things you can do. This is what I teach contractors, right? Number one, window ratings may be unknown, but whether or not a window is low E is not undetectable, right? There are a few tricks you can use. A Bic lighter can give me an indication. Shoot, a lot of low E windows, the ones that are not very expensive, they don't have a huge visible transmittance rating. You look out that window on a sunny day, there's a slight green tint to that window. I'm colorblind and I can pick up on it, right? And I'm red-green colorblind and I can pick up on it. But if you shine a yellow flame, right, that you get like from a Bic lighter in front of a window, the reflection off a low E window is going to be a very different color on that second pane reflection. You can also do this with a white light. So if you have a flashlight, the trick with doing it with a flashlight, you look more professional doing it, but the trick to doing it with a flashlight is making sure the flashlight isn't too bright. You've got to get a dim light coming from your flashlight. And most flashlights, you can $10 flashlight and see, and it's got different brightness settings on it. You can shine that on the window and look at the reflections on the window, and you're going to see one of them's got a weird color to it. It's got a weird shimmer to it. It's got an iridescent kind of a look to it. That's a low E coating. So if whether or not you got a low E coating, you put that in the load and you take the extra time to do that, right? That's why an address can't give you a load calculation. I need a human being to look at that window and shine a light on it or do something to it and tell me whether it's low E. The other thing is whether it's got a thermal break, right? And so and when it comes to the insulation in the walls, or it comes to whether or not there's a thermal break in the window. So technically what you can use is infrared technology, right? Like a thermal camera or a thermal gun, but I can use the back of my hand, man. if you aren't, there's not a lot of HVAC sales calls on 60-degree days, right? These are the slow times for HVAC professionals, right? It's when it hits 90 and when it drops below, 40, we start getting the phone calls, right? So if you touch your hand to the window frame and it's more like the outdoor temperature than the indoor temperature, yeah, there's probably no thermal break, right? If it's more like the indoor temperature than the outdoor temperature, it probably is, right? And if you have an old enough home where you're not sure if there's insulation in the walls, same thing, right? And you can actually do a better job of it by taking a surface temperature reading with an infrared gun on the outside and the inside and comparing the numbers. So I don't have to, and by the way, the third thing you can do, go to an outlet switch, right? Or an outlet or a switch on an outside wall. Remove the plate and take I recommend a plastic crochet hook. I know it sounds ridiculous, but you can get something in between. Like I had a Herzrater come to my house once, took out a drill, wanted to go behind my refrigerator and look at the insulation of the walls. I put that stupid thing away, and we went to the switch plate at my front door. It's here. Let's put a hole here, and a tiny one with something that's got a hook on it. Then we'll pull back and see if there's any insulation in there. Of course, there wasn't. I have an old house. So these are not unknown factors. And yeah, I would say other than that, right? So that's the hard part. That's the biggest complaint, right? That's the thing. Contractors are, what am I supposed to do? Cut a hole in the wall? I'm like, dude, they already did. Don't worry about it. And if you don't want to cut a hole in the wall, use a laser. You'll impress the crap out of your homeowner. So there you go.
I think these next two are going to kind of go hand in hand. The first one, I've heard there's a 10% cushion in the Manual J procedure. Any truth to this?
No. The ACCA is very, very, very big on there is no inherent factor of safety in the Manual J. And in my personal opinion, it's not the opinion of Wrightsoft, not the opinion of ACCA, it's not the opinion of anybody but Alex Meany. In my personal opinion, the only room for that in the Manual J is something called the thermal absorption factor. So you want to get real nerdy, and by the way, I won't, so don't worry. But if you wanted to get real nerdy, you can start talking about, in reality, not in a load calculation, not on a piece of paper. In reality, you can change the load in a room with a lot of glass in it by changing the furniture in there. Heavy furniture can absorb more heat than lightweight furniture, okay? So there's a factor in all load calculations everywhere that takes into account, when you're calculating solar gain, how much heat can be absorbed in the space. It's about the only place in the whole dang thing where you could introduce any fudge. And give them some credit. That is a dead, there's no way they can know that. And there's no way you could ask a contractor to estimate that. And so if they did estimate it on the high side, God bless them. That's what I would want them to do, all right? Because it's a completely unknown factor and not realistic for us to take into account. So what I like to tell people is energy experts are the ones who often say the Manual J has a fudge factor in it. Well, an energy expert thinks a south-facing window is the worst window in the house. Well, that's true if you're trying to measure how much heat or how much energy it takes to heat and cool the home over a year. But if you're trying to make the home comfortable, a west-facing window is much worse, because at its peak hour of the day, that's a worse thing. We look at homes differently. Energy people look at homes over the long haul and don't care about the one little peak. And comfort professionals whose job it is to make you comfortable care most about when you're going to be uncomfortable. And so there's a very big difference in how they look at things, and that's where a lot of that disconnect comes from.
Well, and there's a 15% cooling oversizing allowed by, where does that come into play?
Well, that's Manual S, and if you didn't have that, you'd have to have 3.2 tons. Yeah, exactly. Yeah. You'd have to custom order every air conditioner, like they do windows, right? Replacement windows, they're literally all made at the factory specifically for your house, right? Yeah. You can't do that for air conditioning. Every air conditioner would cost $70,000.
Right,
so
right.
They come in standard sizes, and you do what you can with your standard sizes. Yeah.
Okay.
But that's Manual S. So we'll talk about that next time.
Yeah, I'm looking forward to that one. All right, next one. My concern, more than a question, I've always had with heat loads are fudge factors and getting them undersized which is harder to overcome than oversized. What I mean, windows, walls, other thing, variable unknowns. This has always bugged me. For adding FUD factors to guess to heat loads, it isn't much different than the old rule of thumb. It's hard to get on board with trusting heat loads due to this. You got any comments on that?
Plenty. So the big thing I would say to that, actually, that's not the file I wanted to open. I want to open a slightly different file. So in the absence of a load calculation, like, so the assumption is there's going to be guesswork in a load calculation. I actually don't disagree with that, right? You got me on that one, all right? You're doing retrofit loads. I mean, the biggest one, actually, you didn't even mention the biggest one. The biggest guess is the infiltration rate on the house, right? That's actually the biggest unknown, because I'll tell you what, I can tell you within a reasonable degree what the insulation factor is and what the window type is. Yeah, like a lot of those are known factors to a degree. And actually, fun fact, right? Hold on, let me really quickly here go to a file. This is a little document. No, that's not what I want. I want this. So there. The way R value and U values work, the higher you get on this chart, the less their differences are, because you don't use R values in load calcs, you use U values, right? And so, like, I'm not going to know if it's R, 16 or R17 or R19 or R22. Nobody cares. As soon as you climb up the chart, there's very little difference in the numbers, right? So the difference in R1 and R2 is enormous. Do you have some insulation? I need to know, right? Because the difference is 0.5, right? The difference between 16 and 32 is 0.03. As soon as you tell me your building is insulated, I don't care what is the insulation. What's R11 versus R13? It's almost nothing, right? The actual difference in the load cap. These energy codes that we have, guys, right, that say we got to go to R38 instead of R30, they are not about the difference it makes on one home. They are about the difference it makes on a grid, the entire power grid. The difference it makes on one home is almost negligible. Now, you throw together 10 negligible differences, you get a noticeable difference. But still, it's getting in the ballpark of your insulation value, saying, oh, it's, it might not be R0 or it might be R11. I need a person on site to look. But the fact that it might be R11 versus R13, I don't actually care, right? It's not going to make that much difference. And so instead, because the alternative, right? And so instead of doing a heat load, the old way is rule of thumb, right? And so this is a 2-ton house. Now, I say this is a 2-ton house. I mean, when I do the load on it and I picked the system using manual S and doing all the things right, we picked a 2-ton system for this house and it was the right size. Okay. So these are all 2-ton houses. Okay. They're the same house. I just made copies of them. Right? So that's a 2-ton house, and that's a 2-ton house, and that's a 2-ton house, and that's a 2-ton house. So here's the problem. When you smush them together, this is a 5-ton house. It's not 2, 4, 6, 8 tons. It's a 5-ton house. Half the walls are gone. Geometry of the building matters, and the human brain does not take this into account when we say 1,800 square feet. Right? Because you can have an 1,800 square foot rectangular house, you can have an 1,800 square foot square house, you can have an 1,800 square foot that has 5 additions on it and bump outs, and all of those, even if I assume the same amount of insulation, U value, windows, and everything, all of those give me different loads. Geometry matters in a way that the human brain is not taken into account quickly and easily. It's why you need to do the numbers. And so if you're going to rule of thumb, quote unquote, what your insulation values are, but you're at least going to run the numbers and put the geometry of the home in and the windows direction in which, or how about this, right? We'll take the load calculation that we just did. Shoot, I didn't save it. All right, we'll take a load calculation that I have done and we'll look at the load. So 30,000 BTUs of sensible cooling or 25,000. I don't even change this house. is built the same way. It just faces a different direction, right? You change the orientation of the building, that's 5,000 BTUs of swing right there. That's a different system. That's a half a ton plus some, right?
Oh, while you're on this one, switch back to that previous load.
What the two?
Yeah, right there. No, right there.
Oh,
So looking at that kitchen there, you're showing 178 CFM, and then when you switch to the other load, it drops down, and that's part. I was curious about that, and then I also had a question about how are you getting 178 CFM out of a 6-inch flex?
You're not.
Okay.
Yeah. So that's the thing I was talking about earlier. This is bad duct. This is shame on me duct. Here, hold on.
You did some overrides and some things.
This is all overridden. And by the way, you couldn't if you guys asked for a manual D report, I would not be able to get this past you. Okay. The manual D report would give you a bunch of error values and would give you, there we go. That's what this duct system should be.
So a code official would be able to see
Yeah, if you printed out that duct system, it would just show bold and overridden values and a bunch of zeros where static pressure should be, and it would be all janked up. It would be the weird, like, as long as you're not a code official who looks at the thing and says, well, it says right soft on it, must be good, and sticks it in a folder, you'd be noticing some significant differences. So yeah, and here if I go, let me just change a setting because there. So yeah, it should be 8 for 136. For 178 should be a 9 technically, with 0.2 inches of available static and 200 feet of equivalent length. So yeah.
Gotcha.
Yeah.
All right, just a couple more, I think. Let's see here. Oh, that's all the ones typed in, but I've got a couple.
Yeah.
On Energy Vanguard's blog, I was just kind of reading through. I just get your opinion on this. To me, if I'm an HVAC contractor, especially if I'm working with the production builder, I'm putting, I know I'm going to do 137 of this home design, this exact floor plan in the next year or whatever it may be. Now, granted, we saw how you can add half a ton based on orientation. However, there's only, a handful. What do you think about adding data loggers to equipment to look at run times and to kind of verify that all of this JSD and everything is working together and you're actually getting the moisture removal you are? Just general thoughts on data loggers and double checking your systems.
So I love the idea of more testing, right? Of more analysis. I think the data loggers should look less at runtime and more at indoor outcomes, right? Because
runtime, a coil runtime's not necessarily equivalent to moisture removal, depending on coil system, fan speed, all this.
Because if you said, if you're going to test, right? So this is like it's a very PhD thing to do, to say I want to test, and then what do you test? You test freaking a number. You test a bunch of numbers that are 2 steps removed from what you actually want to know, right? What you actually want to know is the house comfort, maintaining comfort, right? All right, well, give me some indoor temperature and humidity sensors and tell me how much the temperature fluctuates and how much the humidity level fluctuates, right?
Yeah. Right.
Now, I would also like to know maybe what the runtime is, but here is my opinion, Alex Meany's opinion, not the representative of anybody else, but it is my opinion that there is an awful lot of emphasis on that peak run hour. And I get, right, look at California, right? They're at peak grid. They're not even at peak generation problems anymore. They're having delivery problems at peak run hour. But there is an awful lot of emphasis placed on peak run hour in residential homes, which make up a very small piece of the electricity pie. Like, can we just maybe take a deep breath and take a step back and stop sacrificing comfort to that one peak hour of the year until we've done maybe a little bit of something on looking at that very same problem on the commercial side of the fence, where 80 to 90% of my energy goes during that peak hour. Because that is where a lot of this concern, because it has very little effect on the homeowner's energy bill, by the way, right? If you have a few more start and stop cycles, but you are perfectly comfortable in your home, short cycling does not affect energy bills the way they told us it did 20 years ago. They've done tests that has very little impact on the actual energy bill, right? Unless you have have a lot of peak rates and things get a little funky there.
But obviously, massive impact on moisture removal.
It can, right? So let's look at it whether it's doing its job. Because here's what I think. I think if you showed me, oh, look at all the start stops, I think what you would have is maybe a case. Because if you had a system that was designed to do a lot of moisture removal up top, that'd be a very well designed system. But the power companies would hate it.
Yeah.
Right. It's turning on more than I wanted to. We could make this. All I get is guys saying we could make this smaller, right? You could. Why? It's comfortable, right? You can look at the temperature's fine. Like, data log my indoor comfort first and foremost. Yeah. You want to data log the system, fine, but data log the indoor comfort.
At the very end, I want to show you a quick slide that we did for ERCOT on residential load, and this is the last question. What is your opinion on using 105 degrees outdoor design in Texas?
Well, depending on the location, let's take a look at it. Texas is a big state. I'm not going to tell you that.
Yeah. Well, I mean, typically we're 96 to 98. So adding 70. Well, it gets 105 degrees here. That 97, 98, I don't trust. I'm going to put in 105.
Yeah.
Just generally adding 6, 7, 8. So what I answered people when they asked me that, and tell me if I'm right or way off base, is, this design temperature is for 99% of the time. Yes, 1% of the time it's above this, but do you want to design your system based on the outdoor design for handling 99% of the time or 1% of the time? And that kind of also another question, kind of rule of thumb, or not rule of thumb, but I've heard it as a code official, and I know other code officials on the line have heard it. Big, nice custom home going in, and it's got 3.5 tons of load, but they entertain a lot, so I'm going to put in a 5 ton. And I argue, do you want to design your system for your 4th of July party or for the other 164 days a year? So
that is
that in general.
That is a very good way of looking at it. So here's what I was just having this conversation yesterday with a contractor, right? So at 99 degrees, Dallas-Fort Worth that's the 1% design. The average worst temperature of the year is 104, and you guys spend 60 hours, so 54 hours over 100, and almost 60 hours over 100 degrees, 4 hours from 105 to 109, right? So you are 100% correct that if you're designing to 105, so the way I like to say it is, so your system's going to work right 4 hours of the year. Nice job, right? That system is working correctly. It's working the way you designed it 4 hours of the year, right? That's not good, right? We need it to work correctly more often than that. And this is not 99 degrees is not the temperature at which your air conditioner stops working, right? The question always comes up, right? Because contractors, and I get why, I mean, I know really smart people who think this way, right? So if my system's designed for 99 degrees and I set my design temperature for 75, that means when it's 105 degrees outside, that it's going to be 81 degrees in the house. Wrong. That is not how this works, because when we do calculations, oversimplify the realities of the field significantly. We are not physicists, we're engineers, right? We're not even engineers, but physicists do the math on actual model. They model the world, right? And a lot of energy calculations try to do this actually, because there's more, they're more involved. But in a load calculation land, you just want to know what the one time a day is. And so you treat everything as though there's an instantaneous number that happens. Guys, heat takes time. Heat takes time, right? So what I do is I talk to that contractor, and I say, look, you got a homeowner who's got a vacation house. They show up to the vacation house on Friday, right? The air conditioner's been off all week. They show up to the vacation house on Friday. It's been 98 degrees all day that day. They come home, they turn the air conditioner on, and they call you, and they say, we turned the air conditioner on an hour ago, and it's still uncomfortable in the house. Come on out here. What are you going to tell them? Like, that's just not how air conditioners work, man. You can't just turn it on and be comfortable in an hour. That's not how air conditioners work, right? Yeah. Well, that's not how heat works. That's what really you're saying. That's not how heat works. So if it gets to be a couple of degrees warmer outside, it is not going to instantaneously going to get hot in your house. It takes time to heat things up. Now, temperature will start to rise. And so there is, by the way, because if it's 105 or 106 and you designed it 99 degrees and it maintains 105, 106 for a couple hours, it is going to start to get warm in your house. Yeah. So the $1 million question is, what do I tell my homeowner who's going to call on the hottest day of the year? And if I do how many of these systems, everybody's going to call on the hottest day of the year. I can't handle that kind of call volume. You have to be honest with your customers. And if you're going to properly design a system, you may want to talk to them and say to them, hey, if we're going to have a heat wave, turn your thermostat down in the morning. Yeah. A lot of HVAC contractors won't tell you this, right? They'll tell you just put something bigger in here. But if you put something bigger in here, you're going to have moisture removal problems. Turn your thermostat down in the morning. It'll be 70 degrees in your house when the day is nice and cool. When it gets hot, it'll warm up, but it'll stay inside the comfort zone. It'll stay inside your comfort tolerance.
Right. Well, we're about 17 minutes over, so I'll save that slide and share it with you for when we get you back to dig deeper into some of this stuff. I appreciate everyone joining us this morning, and really nice job, Alex, and I'm looking forward to the next one. Shoot me some dates, and we'll get it on the calendar. Thanks so much, everybody. Y'all have a great weekend, and Recom Tech.
All right. Thank you.